maybe 4.0021 or 002150. If the more refined measurement you make, the more digits you have after the decimal point. So that term is fictitious. What it really means is accuracy is synonymous with degree of correctness. So that term, we think about it, but we don't really use it. This is what we use, precision. The closeness of approach of each of similar measurements to the arithmetic mean of the measurements is called precision. In other words, it is reproducibility or reproducibility. So if the measurement is repeatable, if you measure it many, many times, it comes out very close. Well, that's good. That's a precise. That's good precision. If it's spread out a lot, it's not precise. So that's more of a scientific or reasonable way to define the quality of a measurement. It may be noted that accuracy requires precision. If you want to be accurate, okay, if you recognize that exists, it has to be precise. But precision does not guarantee accuracy because you can be completely wrong. You have repeatable measurement, but it's not close to true value. So that is also possible. Resolution is another term that we use even more often. It is the smallest division on the instrument readout scale, or for a digital display, one digit of change of the last digit. So what does that one digit mean? So for digital readout unit, you have finite number or finite resolution. For analog readout unit, you can have many digits after the decimal point. So we will get into that later. It's the analog digital. I don't know if you remember, if you watched a movie called Battleship, something like that. There's some outer space invasion of a Hawaii island neighboring. This battleship got into a war. I shouldn't say war, battle. I don't know if you watched that movie. There's a line that caught my attention. They got into battleship built in World War II. The captain said, we'll sail this ship to the ocean and fight the outer space elements. And the sailor said, we will train on a digital system. This ship is completely analog. You have more appreciation after we get into it. Sensitivity refers to the amount of output response that an instrument or transducer produces when an input quantity is applied to it. How sensitive is it? If there's a scale sensitive to thousands of a gram or 10 grams, so forth and so on. Usually, the sensitivity relates to the range. The larger the range, the measurements, for example, we have a scale that measures thousands of tons, then you'll be lucky if you have a resolution of 1 ton. If this whole range is only 1 ton, then you probably can get a kilograms kind of resolution. High sensitivity does not imply high accuracy or precision. So just how refined the numbers you can get. That's sensitivity. Error, the deviation between the measured value and the true value. So again, true value is the error. A more realistic way to look at it will be we'll get into the closed loop control. You want the system to perform at a certain time to have certain output. The current output versus the output you targeted, and that's the error. It's probably better. Also, of course, the error could be is mathematically equal to accuracy. If you have deviation from what you believe true value is, that's your error. So these are the terms that we will face when we use different measurement devices. Okay, so we get into basics of how do we measure some important physical quantities. The first and foremost is linear displacement. It goes through the list is development, history of development. Dial gauge, if you look at some of the more classic geotechnical laboratories, you'll see that dial gauge. LVDT is probably the most commonly used sensors to measure linear displacement. And we also have non-contact proximeter, and that measures very small movement, like a fraction of a micron. That's displacement. Of course, this is coming out strong. Don't worry about these physical devices, just use image. If I keep taking photos and then compare the pixel positions, then I know how much you move. Of course, if the more resolution you want, the more pixels you will require. So that's another story, which I'm not going to get into in this series. So but basically, we'll look at the first two. Dial gauge is basically just a rod, we call it a spindle, and then inside of this gauge is a series of gears. So this large gear and small gear. So a little bit of movement in a large scale gear will cause a lot of movement in a small gear. So that will give you the sensitivity. So you can look at the more refined movement. So the problem of this is completely mechanical. You cannot automate it. It does not have any electrical output. But that's when I was in undergraduate program, that's the only thing we have. You want to measure, you do the consolidation test. The dial gauge is the only thing. Now, probably in any geotechnical laboratory, you will see this. LVDT, linear variable differential transducer. I think this is extremely creative, very brilliant invention. You have 3 coils and a core, a rod, equivalent to that dial gauge spindle. This primary coil has electrical current goes through that. Electrical current creates magnetic field to this metallic spindle or core, and the mechanical, the magnetic field creates a current to this secondary coil. So imagine if this core moves to the left, then this S1 has more current than S2. So you measure the voltage difference between S1 and S2. That tells you the position of this core. And when this core goes that way, S2 goes up, S1 goes down. So this is why it's called differential transducer. It's always measure the difference in voltage between the two secondary coils. It's as simple as that. So this is very easy to use, extremely linear, and this part can be made completely waterproof, so you can even submerge this sensor in water. So that's why, and nowadays it's extremely cost effective. After, I think this technology was invented in 1950, so it's now half a century old already. It's very available, very affordable. Strain measurement, that's another thing that we often use in geotechnical monitoring, especially in laboratory research. Which is these 3 we'll talk about today. One is electrical resistance strain gauge. That's the most conventional classic strain gauge. Vibrating wire strain gauge and optical fiber strain gauge, which we will get into later. This electrical resistance strain gauge starts from any kind of metal. If you stretch it thin, the Poisson effect makes it thinner or reduces the radius, then resistance goes up. Of course, this ratio between strain and resistance is H factor. That's the basic idea. And then later on, it became the strain gauge that we see today. It becomes a kind of curved shape. It's a printed circuit sort of thing. But it starts with just a thin piece of metal. It started with an unbounded wire on a frame, correctly, wire to whatever you are measuring, of course, then your measurement device will have to be very very sensitive, or it has a very high resolution. Otherwise, because simply stretching the cable, unless the metal is right, the change of resistance is not very high. Bonded wire, bond the wire completely onto the material you want to measure. So these are the more classic ways of measuring strain with a strain gauge. Nowadays, it's metal foil strain gauge. Again, when I was 30, 40 years ago, even that metal foil strain gauge was expensive. Nowadays, again, it becomes very available, very cost effective because it's made by the MEMS technology and all that is mass produced. So it's very cost effective. So that's the current day. A lot of this strain gauge by MEMS. I will talk about the major difference between MEMS and that. This MEMS strain gauge or any MEMS sensor has all the readout unit attached to it. So it's output directly into a digital output. So there's a lot of circuit and devices are sitting. So that's how it can be so cost effective. So, but that's part of history. This is what we learned in high school, at least what I learned in high school. Whistle bridge, right? So that's how we offset the temperature effect. The classic way to have 4 strain gauges, each strain gauge is really just a strain for resistors, and then you hook up back to back into this web, and you have A and C. You input a constant voltage, and you measure the voltage between B and D, and then the input voltage and your measurement of E relates to the original resistance of the strain gauge resistance, and also the change of resistance because caused by the strain. Typical nowadays, the resistance strain gauge usually has a resistance of 125 ohms, something like that, or 250 ohms. So and then we simplify that. This is the equation. You have plus and minus. So when there's no strain, only the temperature changes. When the temperature increases, the R1, all 4 of them change the same direction, but then you have plus and minus, so they cancel out. So the temperature itself does not cause any reading voltage difference. But the strains, if you align it so that when the measurement system you're measuring, when the deformation occurs, one side increases, the other side decreases, then the real strain measurement doubles its resolution. So it's a very good system that can be used to minimize or offset the temperature effect by a Whistle bridge. That's a technique we use often. Vibrating wire strain gauge is a more recent development, newer than resistance strain gauge. This can be seen as a guitar string. If you tighten the guitar string, then the pitch goes higher. If you loosen it, it becomes lower. So this is basically the same idea. We have a coil to sense the pitch of this vibration of these wire, and then we calibrate that against the amount of strain between these 2 ends, supporting ends. This system is much more durable and can be much more resistant to moisture and water. So that's used more often in field monitoring. So that's displacement measurement. I have not talked about fiber optic. Fiber optic goes towards the later part of the presentation. Force measurement. Again, we'll go down in history. Proving ring is the system, the device we use to measure force. When I was in undergraduate program. Nowadays, I don't even see it in any laboratory. because to read the low cell, the measurement device we use now to measure force is mostly electrical resistance low cell. Again, it's a piece of metal with strain gauge attached to it. That strain gauge can be resistance strain gauge or vibrating wire strain gauge. So that's why I put the force measurement behind the linear displacement, because basically the direct measurement is still displacement or strain. So that's a proving ring, just a piece of metal. It's a ring. Then you have a dial gauge in between, so as the ring is compressed by force, this ring becomes flatter, and then the amount of displacement is calibrated to the amount of force experienced. So this is basic idea. Again, if you set up like this, you cannot automate that because there's no electrical output. The electrical resistance load cell is not what we use now, commonly used. You see this four strain gauge alignment. This again is the same idea of Whiston bridge to offset the temperature effect, and in this case, it also offset the off-center loading and all that. So this is a very commonly used force measurement device that we have today. And this is the donut shape load cell. This load cell was designed by Clarence K. Chen. I don't know his audience here today, or at least now in Europe, right? I don't see anyone from California here. No one? No? A little history in geotechnical engineering. Clarence Chen grew up in Chinatown, in San Francisco. He had a master's degree in mechanical engineering from UC Berkeley. After that, he worked with Professor Harry C. But again, if you're not, Europe does not have a liquefaction problem most places. So even if you do not use the Harry C's procedure. He was a very important assistant to Harry C. because Harry C. was 100% geotechnical engineer. He did not know much about laboratory testing devices. Clarence Chen designed a very important device, they call it CKC, cyclic trichome test. Imagine this is back in the 1960s to run cyclic tests on soils to determine the cyclic strength, liquefaction resistance of the soil. And he, along with that cyclic trichome device, he designed this low cell. This is hand drawing. Back in those days, there was no AutoCAD. He gave me this hand drawing he made. Again, you have 4 strain gauges, 2 on the further away, the large ring of the donut, 2 on the other side of it. And when this center part is loaded, you have a movement. This is why I think it's extremely, if I exaggerated, this ring donut becomes this shape. And here you have tension. Here you have compression, or here. Then this you have mostly tension. So this is how you can offset the temperature effect. And also, you have a pair in this way and a pair that way. So you have loading is off-center a little bit. It compensates. So this is a very simple, very brilliant design. And also, all strain gauges are located on one side of this donut. And you can easily, again, so if you look at the geotechnical laboratory, you have donut, you have those, and it's very, you have stress concentration. So the stress measurement, earth pressure cells, was a very popular device in the 1960s. If you go back to that part of the literature, in a lot of publications, including work by people at UC Berkeley, and because at the time the subject of Earth retaining wall is an important subject, believe it or not. So a lot of interest was devoted into what is the lateral earth pressure. So in other words, the best way is to measure it. And the measurement goes very complicated. You have seismic, earthquake loading, so forth and so on. Anyway, after a lot of trials, they noticed these readings are mostly questionable, and then they got into the details. And so this is, of course, the very bottom line is you're trying to measure something that does not exist. Eventually, if you want to really do it right, you measure the contact force. But that, if you grab a handful of sand, for example, that's easily tens of millions of particles in there. That means tens of millions of contact forces. Even if you have just one direction to measure, there's a lot of measurement to make. So that's why the stress cell in concept does exist, but it's not popular anymore. Of course, instead of having a pressure sensor on the outside, you can attach strain gauge on the inside. This is vibrating wire. This is a strain gauge. Similar idea to measure stress, or think we're measuring stress. All right. So far, we only talk about the measurement device itself. How do we automate that? In order to automate it, you normally use a computer. But nowadays, we don't have to use computer. There are much easier devices to use. This is a good example I would like to give to the class. Let's say nowadays the missiles are automated, obviously, right? You want to fire the missile and then shoot to hundreds of kilometers away. In order to automate that, obviously you need a computer in there. Imagine if this computer is run by Windows. The moment you want to hit the button and fire the missile, the computer's down, right? So that's how good that is. So obviously we need something much more robust. And this technology is available even for laboratory use. So we'll get into that. To me, the automation is even more powerful than if you hook up into a control system. And they can really completely make your hands free. You can just set up, let's say, for example, consolidation test. The old days, when I was undergraduate, we used dial gauge. You copy it. 4 seconds, 8 seconds, that's pretty fast, pretty intense. And then we have automated data logging. So the computer will take care of it. Just put the weight on, forget it. Computer will take readings for you. But then you still have to put the weight on. That's why the weight, the time is 2 o'clock, 4 o'clock in the morning. You have to wake up and put it in. Now, later on, the computer says, we can do it for you. Computer will adjust the consolidation pressure. So that's completely automated. But anyway, that's the easy way, because that's the slow automated testing. What you really need the control is, let's say you run cyclic traction testing, where you create loading sine wave. And then you cannot, this is impossible for you to control by hand. So then you use computer control, right? The older generation is called open loop. We don't closely monitor it. Just we set a goal and let the system go by itself. For example, let's take the consolidation test I talked about. Well, this is 1 kilogram, put it away, and then 2, and then 4, 8. Once you put it on, I consider it constant. It does not change. In a way, it does change a little. So a better way to do it is the closed loop. I put 1 kilo on it. I keep monitoring the weight. Use a load cell. If it's going up or down because of temperature, of course the beam level changes, so forth and so on. So that's a closed loop. You keep constant watch on your quantities and then adjusting it to make sure it is as accurate as you want, the way you set it. So that's closed loop. Nowadays, it's pretty much all closed loop because the technology is so available. If I go back to the CKC traction device we built in the 1960s, it was open loop. But if you look back in history, in 1960, to build an open loop control traction device was something. If you, again, interested in looking back in history, in the 1960s, there was a big competition between MIT and Berkeley on cyclic traction test. In MIT, the way they run cyclic traction test, or the pendulum with a mass, it's also open loop control. Imagine it's just like a clock, right? Your pendulum, you raise it and then you release it, and your pendulum goes, goes back and forth. That's the cyclic law they apply to the soil. That's how they created it. And CKC has a pneumatic system, which is much more advanced than MIT. Okay, that's, I mean, just if you're interested in that part of history, you can go back and look at the old literature. Now, this is modern day closed loop control. This goes beyond just monitoring. In order to make closed loop control, in order for the computer to get involved, you need to turn whatever reading you have into digital. Computer only recognizes zeros and ones. Binary, right? Whereas a lot of the original transducer's output is voltage, or mostly voltage or current, amp. That's analog. Remember the movie I said? The soldiers were trained on digital. They didn't know analog systems. So the transducer direct output is analog quantities, or mostly. So you have to convert it to digital so that a computer can understand it, can accept that. Think about this conversion as you have a bucket of water. This bucket of water maybe has a little bit of a history. In the 1960s, before 1970, when the United States shot rockets, shoot astronauts to the moon, the analog digital converter, the most state-of-the-art, most advanced analog digital converter, had 8 digits. So 8 bits, or 2 to the power of 8. You can do a calculation. You see how rough it was. But that was enough to send astronauts to the moon. Okay, so after the analog readings are converted into digits, then they can be fetched into computer. Nowadays, mostly it's personal computer. But then, wait a second. If you go to the construction sites, a lot of times the data logging system does not involve the computer. Right? It's a Campbell 10, something like that. It's just a circuit, just a little box. That's actually inside of it is what we call a field programmable gate array. This is what the cyclic loading. Motors, all kinds of motors, DC motors, servo motors, stepper motors. I can see an improvement or change. Let's say aircraft. The modern day aircraft, the jetliners, the flat controls are mostly using servo motors. In the older days, even though the aircraft is still the same, 47, for example, that's used hydraulic motors, hydraulic system, which is much heavier. You need a lot of hydraulic fluid, hydraulic pump, so forth and so on. But that's, I'm not going to get into this motors and all. This is to control the hydraulic system. Hydraulic actuators, the servo valve, the proportional valve, that is to control the flow rate of the fluid or the position of the actuator, so forth and so on. That, if you put in the effort to do the programming, do the data, the measurement part of it, and the control part of it, and form a loop, eventually, I say eventually, you can accomplish a fully automated control system, closed loop. In the control part of it, you have to decide. I mentioned a lot of things. The force is not high enough. You need to increase the force. Or the movement is not low enough. We need to increase the movement. So how do we assign the magnitude? You should go 1 centimeter or increase the load by 10 kilo, 5 kilo. There's theory behind it. I don't know all the details. I just know this much. PID control, proportional, integral, and derivative. This is the basics of, there's a discipline called control engineering, right? So that's what they learned in 4 years. So basically we know from common sense, the larger the error, the more adjustment I need to have, right? So this is what this proportional is all about. Okay, we assign a constant, Kp. But then, how fast do you want to go? Let's say the load is not high enough, I add 5 kilo to it. And then for how long? For 1 second? For 10 seconds? For 0.1 seconds? So that's the integral part of it. And how fast do I change it? So in order to do a very nice control, let's say you want to do static interaction test, a good sine wave, all these three PID constants will have to be correct. And for us, nowadays, this PID control is very available. Commercial software you buy for laboratory testing, they come with it. So I think it's better if we know something about it. So this is once you assign these three factors, then the computer will automatically adjust according to your KD, KI, KD, and then make the amount of adjustment there at a very high rate. The adjustment is much faster than the integral part of it. When you maintain this load for 5 seconds, then the computer goes much faster than 5 seconds. So keep track of the adjustment that you assign. You just take a quick look of what happens. Let's say if this is the ideal kind of trace that we want to maintain a physical quantity. Let's say for example, this is force. At this moment, I want the force to jump into this level and keep it constant up to here, and then drop to 0 and go down. Actually, it's impossible to do it because anything happens, it takes time. So in reality, this will be as good as, or a fairly good curve. Real measurement versus the ideal target, right? So the next question is what the PID affects. If I adjust proportional gain too high, if I'm too jumpy, so to speak, and then you see this large fluctuation, and then another direction too. Whereas on the other extreme, if P is too low, your response is too sluggish, this is what happens. So of course, then that's just the P. And then what about I and D? This is the correct proportional gain, adjust the derivative gain to reduce overshoot. So you lower the overshoot. In other words, don't make it so fast. But if the derivative is the correct proportional and derivative gain, adjust integral gain to remove static error. Right? If the derivative and integral constant is not correct, you sort of never really close the gap. So that's again another thing you need to adjust. So integral gain too high. In other words, you make one adjustment, you keep it that too long, then you overshoot and then overshoot. Integral gain too low, and it's too slow. So these are the things I can see my grad students spend day and night to adjust their PID. Once it's done, it's perfect. Everybody's happy. The test is very beautiful, nicely done. Okay, I don't know if you noticed, I say this is too high, that is too low, this is too far, and it's not too short. That's not quantity. I want exact number. You tell me 5 kilo too low, 10 kilo too low, 2 centimeters too short, and that I can make adjustment accordingly, right? Instead of using quantitative terms, this is too low, too high, too low. But that's how we think. This is what fuzzy control comes in. I actually wrote a paper on this in ASD and Geotechnical Testing Journal. I'd say if you want to run K-naught consolidation test. Consolidation test, you increase the vertical stress and you monitor the lateral horizontal strain, right? When the strain increases, so it's like the sample is expanding, you increase the lateral stress, push it back. The question is, how much to push it back? What is large? You say, well, this lateral strain increase 0.1%. Is that big? Or is it low? Or is it 0.1 is too large? See, that's immediately we run into problem. What is large, what is not? So that's what fuzzy logic is all about. We build a link between the qualitative thinking and quantitative measurement. And then we call it this membership function. When it's 1, it becomes exactly. When this is large, this person is heavy. Weight is 500 kilos. That's definitely heavy. That's 1, right? When I say, in my case, 70 kilos heavy, well, you gotta be more courteous. This is not that bad, right? So the function, membership function is probably 0.2, 0.3, right? So, but then this is all the model. We set up a scheme to convert or to relate qualitative thinking to quantitative measurement. So if I plot it in a waveform, in a graphic terms, see, this is 0, this is right on target, right? This is positively large, small, positive, medium, positive, big, so forth and so on. And then you establish this membership function, and then you write a program, then you can say, okay, if this is too large, positive large, increase the stress. If it's negatively large, you lower the stress. So again, the question becomes, how much do you want to change? Largely change or small number change? And that's another set of membership functions. So with that, you can do a lot of interesting controls without the involvement of PID. For a while, there were washing machines, this is fuzzy control. There's oven, fuzzy control. There's even motorbikes, fuzzy control. But anyway, that's the idea. Instead of PID, we use fuzzy logic that can also be used in geotechnical monitoring and control. So, how do we do in time? Good. You would like to have a 10-minute break? Good idea, isn't it? And one dedicated signal cable for one sensor. So for a typical strain gauge, you have 4. You have 2 wires for power supply, 2 for signal. So that's 4 wires for one strain gauge. So that's quite a lot. If you have a lot of sensors for some field measurement, for example, again, if you're interested in looking at some literature of earth plane monitoring, there are so many sensors, so many cables. You need to dig a trench just to bury the cables, because the field monitoring cable is at least as thick as your finger. So I mean, when you have a few hundred of those, even sometimes thousands of it, you need a trench to bury them. So with these technologies, fiber optic and MEMS, now you get into another category. One is called partially distributed. Many sensors can be mounted on a single signal transmission lines, and we are able to detect which signals come from where. This technology was borrowed from telecommunication system. We have one optical fiber, and along this optical fiber, you have hundreds of landline telephones, not the cell phones. Cell phones are wireless. The landlines are wired. Even when you have wires, you can have hundreds of landline phones connect to a given optical fiber. So this is called partially distributed. MEMS, it's sort of, but it's wireless. You have one server, then you have different sensors. They all communicate wirelessly, and then connect to the given server. So this we'll get into that later. Of course, the best, the most ideal sensor system is what we call fully distributed. It's like our nerve. Any place in your body, if you pinch your body, you know, feel the pain and where it came from, right? And it just doesn't matter where there's a sensor or not. This, well, partially distributed, you have to pinch your sensor locations, otherwise there's no feeling. So this is the best way, but the technology to a certain degree is there already, but I think it's not ideal yet. It's called Brillouin optical time to make spectrometry. Brillouin is French name, invented by a French scientist. So that's the basic. I think the major breakthrough from electrical to optical fiber or MEMS. The framework of fiber optic sensing, we basically borrow the system from telecommunication. The telecommunication systems start with light source, optical transmitter, usually laser light. And it shoots into the signal that into communication lines, which is optical fiber, that carries the whatever, the data, the voice, the image, whatever you want. And then this channel, that's the optical fiber. The optical fibers are so cheap. The 1 meter of optical fiber, the bare fiber, is probably 2 cents, 2 pennies, US dollars. That's a little less for euros. So that's how cheap it is. And then it has a lot of capability of transmitting signals. And then on the other end, you have a receiver. You convert the optical signal into, again, for electrical systems, you have analog digital conversion. For optical, you have optical electrical conversion. You convert the signal from this end from electrical to optical. And from the other end, the optical means laser light. And when the receiver end, you convert the optical back into electrical, so we can see the image, you can hear the voice, so forth and so on. So that's the basic idea of optical telecommunication system. For optical sensors, we condense all these things crammed into one box. Transmitter, light source, and the optical receiver, the other, is all, of course, miniaturized and put into one box. And what's exposed outside is optical fiber. In their optical fiber, we have sensors. And that can be a lot of them, because that can be partially distributed or fully distributed. So that's the basic setup. There's a lot of advantage when you transmit signals with optical fiber. First of all, it is immune to electromagnetic interference. For those who have done laboratory testing using electrical sensors, one thing that annoys you, or annoys me at least, is the electrical noise. When you turn on the light, there's a 60 hertz fluctuation immediately. And there's all sorts of noise, electrical noise, because they have electromagnetic interference. But when you transmit signals with light, it does not exist. And also, when you do field monitoring, if you put electrical sensors in the field, when there's lightning, you can easily burn your sensors, not just sensors, your cables and your computers also. So this optical fiber sensing is not affected by lightning either. And it's safe in explosive environment. Let's say if you're in a mine shaft, there's gas in there, it's explosive. When the electrical sensors use it, they tend to generate sparks, and spark can generate explosion. And there's no such thing as short circuit because there's no electrical current flowing in the optical fiber. So that's a lot of advantages. This is especially important for field monitoring, sensing landslide, debris flow. There's a lot of water in there. And it's stable, durable material, and it's also stable, very durable in the signal, because optical fiber is basically made out of glass, which is very durable material. And it's small and flexible. It's not on purposely making it small just to be convenient. There's a reason for that. You need that small dimensions so that the light can be transmitted for a long distance without losing its quality. How small it is, most of the optical telecommunication system, the optical fiber has a diameter of 250 microns, 0.25 millimeters. That's including a coating glass part of it is only 125 microns, so it's very small. This I talked about it, capable of either partially or fully distributed sensing. It can be a nerve system, or at least partially distributed. It's very low attenuation. When you satisfy the purity of the glass and the size and all that, you can prove, you can feel it has very low attenuation. The signal can pass through, the light signal can pass easily for tens of kilometers, at least for sensors. But telecommunications, you're talking hundreds of kilometers easily, and even across the Atlantic Ocean or Pacific Ocean, that will require some amplification, but still, it's a lot more doable than the conventional copper wires. So these are the advantages of optical fibers. I'm going to just briefly go through this Brillouin optical time domain spectrometry, BOTDR. This light, when it goes through the optical fiber, when it's disturbed, either by strain or temperature, it generates a Brillouin scattering and reflects it back from the, again, this optical fiber. So from this device, we send a pulse, very short period pulse. This again, in measurement or in testing, a lot of times we want something to be short. This pulse has to be as quick as possible, but not too short. If it's too short, then the signal becomes weak, and then we will have a hard time to distinguish or analyze the data. So the optimized duration of this pulse is a matter of design of the whole system. I'm not going to get into. But when part of the optical fiber is stretched, it's creating strain, either by mechanical reasons or temperature, it generates a reflection. The intensity of the reflected wavelength wave, the Brillouin scatter wave, and that relates to the amount of strain. So we can determine the amount of strain or temperature change by the optical frequency, the Brillouin frequency. And also the arrival time of the backscattered light times this velocity of light traveling in glass, which is 3 times 10 to the power 8 meters per second, extremely fast. And this is good and bad. It makes it determination of where the event occurred rather difficult, because you need to cut the time into very, very small range. Otherwise, your space becomes very unreliable. And also, the strain resolution is not as ideal. But basic idea that you can use the whole optical fiber as sensor is attractive. Some people say it has infinite resolution, spatial resolution, where wherever the strain occurred, we can detect that. Now, but then exactly where it occurred is a different story. A typical device like this can determine the location by within accuracy of a few meters. Some extremely expensive ones, they could tell, well, we can determine the event within a distance of centimeters. And also, at least the machine I bought more than 10 years ago, to take one run of readings takes about a few minutes. It's very slow, so you forget about dynamic monitoring. Nowadays, you can do dynamic monitoring too. So again, but that's expensive. In any way, you can easily measure monitor what happens to this optic fiber for a distance, at least 10 kilometers. It's a very long distance. So that's the power of this fully distributed BOTDR technology. I'll just show you a good example. This is from UK. Professor Al-Shafiq, he gave me this PowerPoint, the job they did at Cambridge University. This is a monitoring of a diaphragm wall. I'll show you the shape of the diaphragm wall. It's very big structure. This is an Abbey Mills pumping station. These people from UK probably know that. 84 meters deep. So the measurement of the lateral deflection of wall induced the strain. And these are the BOTDR strain readings, and that's the plexus projection of the strain distribution of that wall. So with this kind of system, it's rather easy to set it up. All you have to do is to tighten the cable into the strain and the steel reinforcement. That's it. And you lower the whole cage into the ground or the canopy, and you have readings. I think one of the presentations in my session about monitoring talk about that in German. All right. That's BOTDR. That's basically the state of the art. They use it a lot in bore piles. Why bore piles? Because then you have a chance to lower your steel cage reinforcement, and then along is the reinforcement is your optical fiber cable, and then your bore concrete. Driven pile, that's easy. That's more difficult. You have to attach the optical fiber into your pile when it's manufactured in a factory. And driven pile, they usually involve some cutting and splicing. So what happens when you cut the pile, you cut the optical fiber too. Or splicing, you need to extend the cable, which is complicated. Anyway, so that's BOTDR. This is another type of optical fiber grading sensing technique. We call it optical fiber bright grading, FBG. This is the one I use the most, even though I also worked on this BOTDR when I gave it up after a few years of trying because it's just not easy to apply. Not to mention it's extremely expensive. I think the cost has not come down. A typical BOTDR readout unit costs probably around 100,000 euro. So that's a very high cost. Whereas this FBG readout unit is probably less than 10,000, right? So the basic idea is this. This is we call it single mode optical fiber with the total outside diameter 250 microns. Inside of it is only 125 microns. The outside coating is just acrylic, plastic for protection purpose. And FBG is made in a section about 5 to 10 millimeters distance. The change is, we call refraction coefficient, periodically. Almost like when you go into a beach. Let's say you put your hand on your arm and exposed to sun, like this kind of sun is good enough. For 30 minutes or so, you take your hand off, you see when it's covered by your fingers, it's light. It's not covered, it becomes dark, isn't it? So, this is a similar idea. You put we call it a mask. It is this, with this extremely thin strings. For that, usually 5-6 millimeter distance, there are at least 10,000 of those fine strings. And they expose that part under extremely strong ultraviolet light. So then you create this dark light, that kind of period. This space between the dark and light, it's not necessarily really dark and light, just changes the refractive coefficient. We call it grading period. It's capital lambda. When the light source comes in from here, usually we call it harmonic light. It's laser light with a wide range of wavelengths. When it hits this FBG, part of it is reflected back. The reflected wavelength is related to this capital lambda. So when this part of the FBG is stretched, this lambda increases. Then the refracted wavelength increases. So we use the wavelength shift to determine what kind of strain this part of the FBG is experiencing. That equation roughly is spot here. The change of wavelength is equal to about 1.3 picometer per microstrand. The current readout unit can detect wavelength shifting of 1 picometer. So you can roughly say what we can detect strength variation by 1 microstrand, which is very, very good compared to BOTDR, the full distributed strain measurement method can have a resolution of about 30 to 50 microstrands. So this is much more refined. And also the temperature change. The temperature can cause the glass to expand. So for every degree of Celsius variation, it changes 13 picometer of wavelength because the strength is reduced if you go through the thermal expansion coefficient. So in other words, for FEG, we can use it as a thermometer. We can detect about 0 point something degree resolution. So, and this equation, because this lambda, the shift of wavelength, is linearly related to capital lambda. This capital lambda relates to strength. This n is the refractive index. For glass, optical fiber is about 1.5, a little less than 1.5. This inside of the glass, the refractive index is not exactly a constant, it's a curve. It's low and high and then down. This arrangement is to make sure the light is fully reflected. In other words, unless you bend the fiber extremely curved, otherwise the light will just keep reflection, is fully complete reflection inside of the optical fiber. And how to make something this thin and still have a variable refractive index? That's a very interesting question. If you're interested, you can get on the internet. This technique was invented by Corning, a very famous company. And I visited that place about, I don't know, 16, 17 years ago. It's a very interesting way to do it. But I'm not going to spend the time to get into that. With that technique, imagine you can produce this optical fiber so cheap. So actually so cheap that made quite a few of these companies out of business. Okay, so this is the idea. So every one FEG has sufficient difference of capital lambda from the next one. So the light comes into the single optical fiber, and reflected light has enough distance of wavelength from the next one, so they do not overlap. So you can comfortably determine this reading is come from certain FEG. Right? So typically now we can hook up at least 5, sometimes 10, depends on what you're measuring. The more strain the part of FEG is experiencing, then you have to space them all further apart. Otherwise, you can have more. Right? Of course, the other reason we don't want to have too many is because once the light, laser light passes one FEG, the light intensity becomes lower and lower and lower as it goes. So if you have a lot of them, at the end, the reading will be very weak. So this is the idea, why we can have multiple, why we can have partially distributed system. But so far, when we look at, well, FEG is only strain gauge, isn't it? What about other physical quantities I want to measure, which I'm going to get into later? So at least this is the basic setup. Believe it or not, about more than 10 years ago, I asked my master student to build this thing for me, a geotechnical graduate student, to build this whole system based on whatever material we collected from literature. Actually, it can be done. It's not that difficult. Anyway, so it's done. All right. It's more than that. The wavelength of the light shoots into the optical fiber and meets a FEG and reflected back. This is the original signal you see. Let's say in this case you have 3 FEGs. Like I said, when the light passes through one FEG, it becomes weaker. So the signal is not as strong and it keeps going down. Right? And also, intuitively, you think this is the wavelength reading, right? So, okay, this is low and this is middle and this is high. Is that the case? No. This is the sequence. Every time we shoot the shoot the light, this is not like DOTDR in pulse. This is continuous shooting. So just when I start taking readings, every time I start scanning the reflected wavelength, the light wave, usually it's about 30 to 50,000 data points. In other words, this is only the sequence of the data point that I received back from the optical fiber. The first peak occurred, let's say here, and then 4,000, 6,000, this is 8,000. Let's say this is 7,500. So what is that wavelength? The 7,050 is only the sequence numbers, and then the next one is, let's say, 13,500, so forth and so on. So what is that sequence correspond to in terms of wavelength? This is good and bad. We use we call it wavelength reference. Whenever we take readings, we split the light one into the optical fiber that has the FEG sensors, the other one to this wavelength reference. Wavelength, in this case, it was a little gas chamber. In that gas chamber, it absorbs lights in certain wavelengths. What's left is reflected back or passed through the chamber. The important thing is the peak that passed through the chamber has a very unique wavelength. It's the gas, it's the chemical optical reaction. So this wavelength, every peak is known. So you can buy, the manufacturer provides you a list. So this you can, or a computer, is sort of a data sheet you can feed into your computer. So then this sequence number are the same here and there and there. So whatever this sequence is, you look into here and you check its wavelengths and use that, the peak value, to interpolate the wavelengths. The important thing is this reference wavelength does not shift with time, does not change with as the light intensity becomes weaker, does not change when the optical fiber becomes old. This is why FEG readings does not drift. As electrical sensors, most of them tend to have zero shift or drifting of the readings. The FEG does not. Extremely stable. This is a very important reason why FEG is good for long-term measurement. Of course, then with that, we know, in this case, I have 6 sensors. These are the peak. And then we go through the reference, we go to the peak wavelengths and determine its the wavelengths, and then it depends on what kind of mechanism we're using. We convert that into physical quantities. In this case, it's just like in kilometers. I'll show you how to do it. We have an FEG inclinometer, and this convert from wavelength to strain, from strain to inclination, and if you integrate that, it becomes ground level displacement. So that's the basic idea. Now we'll go through some application cases. We start with the easiest way, is using FEG as strain gauges, and then FEG as part of the transducer. Remember, we can this FEG, and this is inclinometer. Inclinometer, conventional inclinometer is used electrical sensors, which is accelerometer. In this case, we use mass, gravity, to measure the amount of inclination. The rest of the principles are all exactly the same. You integrate the inclination and calculate the level, the movement, accumulate that into level displacement. This is FEG extensometer. This part is just for demonstration. This plastic tube, you can see what's inside of it. It measures this was developed to measure ground subsidence at different depths, very deep depth. up to 100 meters. We measured up to 150 meters, buried in the ground, so that when the ground settles, it drags this part of the piston. And inside of it is a FBG. Essentially, it's a diaphragm. When movement occurs, it bends the diaphragm to different degrees. You use that to detect the amount of displacement. I'll show you some case of applications. Pressure sensors. This is probably we made the most. Over 1,000 of them already. From very large one, this is extremely sensitive differential pressure transducer. We can measure the water fluctuation within a fraction of millimeters. This is the coil. You can see how big it is. This is regular size. You typical measured pressure in the range of a few hundred kPa. This is a miniature pressure transducer. It's like a 12 millimeter length, 7 or 8 millimeter diameter. This we make specifically for centrifuge, physical modeling test. So we can bury this small sensor along with this tiny little cable, optical fiber cable in physical models. Low cells. This is, remember CKC low cell? Similar design, except the strain gauge is now replaced with FBG. And also, the similar design can be also used to make a pressure transducer. So that's low cell. Again, this you don't have to worry about waterproofing. There's no sealing, no oil infill. It's just whatever it is, sink your water. That does not affect this performance. This is what we call a Amitabh Accelerometer. This is probably the most popular design in FBG accelerometer. This is basically a mass and spring kind of design. The natural frequency is controlled by this stiffness of this spring, and is the glass fiber stiffness, and then the mass. So of course, the softer the spring, the heavier the mass, the lower the natural frequency. This is still not very reliable yet. It has the sensitivity, it has the resolution, but it does not have the durability. If you drop it to even just from a few centimeters, few tens of centimeters, you can easily damage this transducer because this mass is usually pretty high. This we call it optical level beam. This is mainly to measure the very mild fluctuation degree. This they use a lot in railway tracks, especially MRT lines. If you have one MRT line and another one, tunnel is going down, you want to make sure this construction is not affecting this level. So this gives you some idea. This is 900 hours, so that's 30 some days. This you can see it's very extreme stable. And this we set in the room just to verify its stability. It's fluctuating within 0.01 plus minus 0.01 or less than that. If you look at it, range plus 0.005 degrees, something like that. And this is the tilting, or this is sort of in between tilt and a very simple accelerometer. Again, this is mass and the spring. You can use it as a simple accelerometer in addition to a tilt sensor. Some applications. This is now into geohazards monitoring. We developed a stress-based slope stability monitoring and warning system using optical fiber. The most important part of it is the pole pressure measurement, but not just one, but a profile, a lot. We estimate the initial state of stress, assume a plane strain, linear elastic, total stress analysis. That's very simple. I believe everyone in this room can do it. We use that as a starting point, and then we do, let's say, in situ test or lab test to determine the strength parameters, and we establish the failure envelope. And we assume a constant shear field stress path. In other words, when the rainfall starts and rain comes, the pore pressure increases, the stress path moves laterally, and P prime decreases. As it decreases enough, it touches the failure envelope, then you have a failure at that point on your measurement. Oops. What happened? Oh yeah. So we can use that as a warning based on proximity of P prime Q to the failure envelope. This is the place where we install for those. Oh yeah, okay. This is the cross section where we do analysis. This is Alishan. For those of you familiar with Taiwan, it's a famous resort area. About the eastern half of the island is occupied by steep mountains. This is why Taiwan has a lot of landslides. And Taiwan also has earthquake, which shake the ground, make it look weaker, and then typhoon comes with the rain. So then when every typhoon usually induce a lot of landslides. And this was the right after we did this instrumentation right after major landslides. Right, this thing goes automatic. So this is the cross section we were monitoring. We have done a lot of other monitoring I'm not going to talk about. This is the one we did that used the fiber optic pore pressure sensors. This one was like 60 meters deep. And in that 160 meter deep borehole, we put in 10 piezometers, 10 pore pressure sensors, all FDG. Conventional open-end piezometers, well, a typical 10 centimeter borehole, you can probably put 2. That's it. And you need sealing in between all that, but sealing is the same. For those interested in this papers in the reference list, published in 2012. So you have 5 meter spacing between these piezometers. This is automatic. This is what before its installation. The plastic pipe is just the spacing because the space is 5 meters. So every 5 meters you have a piezometer. This is non-woven geotextile, just used as a filter. There was a major typhoon, Maraca, this 2009, August. The amount of, if you add them all up, the amount of rainfall in total is like 2,700 millimeters. I don't know what's the rainfall here in Vienna or Austria. Probably a lot less than that, isn't it? Imagine that kind of rainfall in 3 days. So that this is the regional total stress point according to our linear elastic analysis, and then you subtract the pore pressure measurement at that depth. So as the rainfall continues, the pore pressure increases, the stress points move laterally towards the failure envelope. Of course, good thing it did not fail, but this is just the hypothesis. If the shear strength, which was crushed rock back at site, was 40-degree friction angle, it would have failed. At this depth, this is the shallow depth is here, the deeper is here. And it's square is about, I should not show the depth, about 50 some meters depth. And also, you can see the stress points are usually, oops, why is it happening? Very close to the failure, even without the rain. This is why, those who are in the conference, Professor Charles Huang talked about, over 90% of the landslides are occurring in shallow slopes. Very shallow. Why? because the stress points are very close to the failure envelope, even without the rain. And as a matter of fact, for steep slope, the total stress point is to the left of the failure envelope. Why it did not fail? Because the suction, it brings it back, which we'll talk about later. That's another way of doing it, the monitoring. In other words, with the help of MEG sensors, we do profile measurement. For pore pressure, which is the most important parameter to me in geotechnical engineering anyway. So that's a very good application. This sensor we monitor continuously for like 6-7 years again. So it's very durable, and it's a very powerful way of monitoring, and you can attach to very simple stress model. Probably you can do more. I'm just using the very basic linear elastic model to come up with the initial state of stress, and then you subtract the pore pressure to get your effective stress point. Ground subsidence, which is a major issue in the western part of Taiwan because of the water pumping, groundwater pumping. And this region is here, about southwest of Taiwan. The soil, the depth of soil is easily 600 and more. In some places over 1,000 meters. It's made of very compressible, silty sand, unfortunately. Why is this unfortunate? Because the silty sand is rather permeable, so it's very good to pump water. It's easy to pump water, but then as soon as you pump water, it settles. And the response is very fast. The total accumulated settlement in that region is estimated over 2 meters in the last 20 years or so. Unfortunately, this is also the high-speed rail going through that area. So there's a great concern of the safety of the high-speed rail line. Remember I said we can have multiple sensors on a single line. That sensor does not have to be the same type. So in this case, we have 10 meters spacing. Every 10 meters, we have a sensometer measure vertical ground movement, and then missed by 5 meters, they have another 10 centimeter sensors, pore pressure sensors. So we have one borehole, in this case the borehole is much bigger, we can measure the ground subsidence along with pore pressure variations. So if anybody is pumping water, we'll know it. And then we can detect the status of the ground subsidence. So this is my grad students, they're very excited about this installation. We don't need that many people, but just to show they're dedicated, so they are showed up. So this is the measurement. You can see this is not your typical ground water lowered, groundwater, and then soil mechanics textbooks say, well, groundwater table is lower, that part of the soil becomes heavier, therefore creates more stress. Therefore you have consolidation. First of all, there's no clay in there, mostly sand. If you look at this, the profile. So this is subsidence. Fortunately, that part of the pumping is mostly stopped, so it's a little bit of heating here, although very small. And this part is still pumping. The farmers are still pumping, so it's still subsiding. And this is the state of pore pressure profile. You can see this is the hydrostatic line. That's the long-term groundwater pumping is remain. What happens of groundwater pressure? It's lower than hydrostatic line. That's why it's caused by the pumping, right? So part of it is going back already, and this is still down. And this you have we call it the pore pressure higher than hydrostatic is called artesian pressure there. So this is why in the early days it was very the farmers love to pump water. In some places you don't have to pump; just dig a hole and pump water will shoot up from the ground because it has artesian artesian pressure because it's sloped to the ground. It is on the west coast, and the east side is very high mountains. Then if we hook up the automated data logging, you can see when the farmers are pumping. This, the green curves are the red curves are the full pressure fluctuation. The green are the subsidence at different depth. The green one, the fluctuation is very, very small. That's just the fluctuating readings. The full pressure you see in the morning about 5 o'clock in the morning to 10 o'clock, you can see a dip of full pressure at about 30 meters below ground. And this is the afternoon. So the farmers, they irrigated their rice paddy in the morning and afternoon, turn on the pump. This is 30 meters, this is 40 meters. It's further away from the pump, therefore the fluctuation is less. And it's shallowed out, there's not much of movement. So this gives us a lot more detail. What happens in the ground? What happens, actually we came up with the theory. I don't know if anybody here is doing the shakedown theory. For this type of soil, the ground subsidence is not your classic soil consolidation. It's more like a traffic load, going on and off, on and off, on and off. You start pumping water at least twice a day. And you keep going it for a long time, just like traffic running on pavement, it creates running. That's what happens to the ground subsidence. But anyway, that's a different story. Just tell you what we can do with this fiber optic sensing. And we did similar things in Drone Island, in Singapore. This is in collaboration with Deltaris, the Dutch Research Institute, to install similar things. In Drone Island, which I'm not going to get into details, this is a field. They are also interested in pumping water for freshwater supply. There's a shortage of freshwater, severe shortage of freshwater supply in Singapore. So wherever they can pump groundwater, they would love to do that. But in this case, they don't want to make ground subsidence. So that's why they need this monitoring. All right, so another issue. This is very exciting development in Taiwan. There's currently investment of over $30 billion in this region, just west of the region where I did this ground subsidence monitoring, to build close to 1,000 wind turbines, huge wind turbines. These 5 megawatts power, those huge ones. There's a lot of investment, so obviously they're curious about how safe it is to build these offshore structures. At the moment, there are only 2 wind turbines and 2 meteorology observation tower, we call a mat mast. To take advantage of the mat mast, we put in feasibility, the tilt sensors. So the reason for that is to evaluate feasibility of using MEG transducers for long-term offshore wind turbine monitoring. So if that works, it should work all through the turbine too. And then we can back calculate the stiffness of the soil. So because that region, the soil is not like the North Sea offshore wind turbine. The North Sea soil is clean quartz sand, extremely dense, very feasible for offshore foundations. Not in that region, Taiwan River has a compressible, silty material. So this measurement should reflect the overall performance behavior of the soil. So this is the view of the mat mast from a distance. The sensors will place here at the platform. The platform is about 20 meters above the sea level. So my grad students will also have to climb the ladders. Our students go to the mountains and the ocean. That's interesting. And then the tilt sensors were placed on the platform. There are two systems. One is OL beam, the other one is a tilt sensor. There are a total of 8 of them. 2 in the north-south direction, 2 in the east-west direction. this is the way it looks. The tilt sensor, the OL beam, all covered. Whatever the seams covered with ocean, what do you call it? The epoxy specifically designed for offshore environment. All right, this is the in a calm day when in 2017, last year, July. This is the continuous reading for a few thousand seconds. Just pull the readings out. That shows that the tower is waiting with the angle. The tilting is fluctuating within plus minus 0.1 degrees. But that's a very calm day. If we do a simple spectral analysis, it shows two major frequencies. One is about 0.5 hertz, the other is 1.3 or 1.4 hertz. According to my friend who knows more about this offshore structures, that sounds pretty reasonable. And this is the OL beam. OL beam is not very sensitive to instantaneous movement, so the readings are more variable, but less fluctuating because it's stiffer system. If you do a spectral analysis, it's about the same, except in this case. So probably in the future, we're not going to use OL beam, which is concentrated on tilt sensors. So that will be used to offshore tower monitoring. All right, so that's optical fiber. Next, the last section, the last part of it will be, okay, we have 15 minutes to 11:30, okay. That should be enough. The optical fiber is a good pressure sensor. We can make it into a very good pole pressure sensor, but that's to measure positive pole pressure. For shallow slope failure, usually the slope fails in unsaturated state, and unless we measure negative pole pressure, we will not be able to do stress-based warning system. But measure negative pole pressure, typically we use tensiometers. That's a very painful test, monitoring measurement to do, because tensiometer is negative. Pole pressure tends to create, the pressure sensor tends to lose the saturation. And when that's happened, then you lose the accuracy of the sensor. So it's got to be a better way to do it. Before we do it, get into the details, let's take a look at the theory. Roughly, according to Collins' Literature 2004, if we assume soil has infinitely sloped, then you have a shallow failure. We simulate the rainfall, the constant rainfall intensity. This is 8 hours, 24, 23, 39, so on and so on. When the rainfall continues, the soil on the ground surface starts to become saturated with a zero pole pressure. Below that, it's still negative. When the negative pole pressure profile touches, again, this failure envelope that can be calculated based on the under shear strength parameters and depth and gravity and so forth and so on, then you have failure. So that's what we. So we took a simplified approach. We only we do not run SWCC at all. We use a grain size distribution and density to estimate SWCC. The only reason I show this SWCC is I want to show this. This vertical coordinate can be degree of saturation or volumetric water content. This SR, residual saturation, that's when this drying wetting curve reflects this direction, sort of like T100 in the consolidation curve. This is an important part that we use to estimate the unsaturated shear strength of the soil. So, like I said, we sort of follow the Fang and Button equation in 1999, so that it says the suction versus the degree of saturation can be approximated with this equation, with B, C, and D. And then these three are curve-fitting parameters, right? So psi, we only look at metric suction. We don't worry about osmosis suction. So this is the original grain size distribution, and then I'm not going to get into details. You can convert that into this SWCC curve. So that's your estimated SWCC. And also we recognize the original theory says EB, right? In other words, the suction induced additional shear strength is linear. In other words, your suction goes up, your strength goes up infinitely. That's not impossible. That's not possible because when suction goes to a certain point, you have cracks. So the strength deviates from that linear. So this gives a more realistic way of looking at the additional shear strength versus metric suction. So this is the modified equation. It's the original one. This is EB here. Now we replace that with the tangent E prime and then consider, remember, residual saturation. This is another way to look at it, residual volumetric water content. So this gives you a curve, failure curve that looks at the effects of suction. So that's the basic, very brief background of the way we use. Details are published in the paper, probably come out this month, in the Canadian Geotechnical Journal, for those interested. And we assume the failure is infinitely long. So you have failure plank is parallel to the ground surface. The slope has a constant angle, beta. So with that background, we have a mechanics-based warning system. We don't look at rainfall projection. We don't look at it. It's based on ground movement. So we have a sort of empirical way to look at it. This is strictly based on unsaturated soil mechanics. The only thing I did was I cheated on getting this SWCC. So I can actually, based on my measurement, I can get the factor of safety at different depth of my suction measurement. So I can, on a real-time basis, I can determine the factor of safety as rainfall continues. So that's the theoretical background. From sensing point of view, monitoring point of view is a MEMS-based. The important thing of MEMS sensors, to me, there are a few things. First of all, very small. The MEMS sensors are, most of them, are 3 millimeter by 3 millimeter in plane, and the thickness about 1 millimeter. That's how small that is. You can buy that directly, or they can be mounted on a printed circuit board that has all the other devices in there. And the second thing of MEMS is that, remember all these analog digital conversions and all that, the output is directly in digits. You don't have to worry about analog digital conversion. So that's very convenient. And also, there's a lot of hobbyists around the world that they're crazy about these MEMS things. So there's a lot of systems. This case we use is open source. Everything we use is openly available, and no copyright, no patent. All the software is available. All you have to do is buy every part on the internet, and you assemble the free software into whatever function you want to serve your purpose. So the basic idea is you have a microcontrol unit, MCU, sort of like PC. And then you have power supply to keep the things going. All these MEMS circuit boards, they consume power extremely low. They're in milliwatts. So now in this case we have, along with MCU with the conglomerate, MEMS conglomerate, data transmission module, and then we have moisture sensors. So this is what it looks like. This is the one rod, this is 1.795 meters, and you think that's not long, that's too long. For the case we measured, we use now in the field mostly less than 1 meter. Remember shallow slope failure? These parts are made with 3D printing. This is our moisture sensor. embedded in there. So you can easily adjust your design to accommodate your sensors. So that's, in this case, we have 4 moisture sensors. All the others, circuit boards, are inside of this box, and then on top of it is the antenna. This is the calibration of the moisture sensor. We approximate that with a curve. Inclometer. This inclometer now is secondary because the moisture content tells you the safety factor already. That inclination is just to check if they work, if they fail or not. This is the MCU Arduino. I think typically costs, I don't know, like 20 euros, very cheap. This is the antenna, one of the antenna we use. This is the other circuit boards, all assembled, put it in the box, because we have timer to put the system in sleep, to save energy. So these technologies are so available. I'm not going to get into details. And the transmission, you have LoRa, you have different kinds of 3G, 4G, now 5G is on the horizon to do the safe data transmission. Solar panel to provide the power, so that keeps going, and the battery. And then this is the site where we tried the sensor for the first time. This is not too far from my home, 20, 30 kilometers south of Shinjuku. This is the highway rest station. There's a slope right here. This is the result of at least twice landslide here. So this is a critical place, but then the soil left is not a lot. 1 meter deep, you're into rock. So that's a shallow, potentially shallow slope failure. And this is a very steep slope, you can tell. From this slope, you can see the rest station. And then, good thing is this cell phone antenna right here. So it's a very signal, the receiving signal is very strong here because this antenna is right nearby. Easy to just use electric drill small hole, we insert the sensors, and then now to hammer in the ground to take samples, to do grain-size distribution, traction test, to do saturated traction test, to determine drain and friction angle. So that's all it takes. So this is after install the circuit board before you close the box, and this is done. The sample we took from the ground, from the grain-size distribution, this is the projected SWCC curve from the grain-size distribution. The details are in the paper. I'm not going to talk about it now. Just talk about a few rainfall events. 2017, April 11 to 16, there was a rain here. This is inclination, does not change much. A lot of this is wind because it's flexible plastic rock. This is interesting. Look, remember there's a rain on April 11th when the rain caused increase in saturation at 10 centimeters down, 100 millimeter. Look at this. This is fluctuation. Temperature, even in April, it's hot enough. This is at noontime. About over 30 degrees. Why this does not go that high? Because of the rain. Well, this is at 100 millimeter deep. This is what happens at 50 millimeter deep. Also, moisture went up. The fluctuating temperature is not nearly as significant. 70 is even more stable temperature. But the degree of saturation shot up to 100%. Why did it not fail? Because that sensor is embedded in soft rock. So it's, while it's saturated, we had no slope failure. If we go through the equation, put the simulated estimated SWCC to work, the theta R, this is the direct measurement. This is the HC, the capillary head, converted from the measured moisture content. This is from traction test. This is the slope, the angle. This is density of soil. or unit weight soil. So this, we have all the parameters to calculate real-time factor of safety. So this is the rainfall, and you can see at the lowest level, 70 centimeter down, you have factor of safety down to 1. Oops, this is 2. No, this is not the heavy rain yet. This is the April one. So this this one. That's 1 because this is soft rock. Actually, freeze prime is much higher than that. That's why in reality it did not fail. These are the red is 10 centimeter deep, the blue is 50 centimeters. So whenever you put these sensors, then you can calculate the safety factor at that depth. So this is a different version of sensor. We call it smart stick now. This is one moisture sensor. This is a barometer. You can put this is a rain gauge, all kinds of things. Just one device can be a weather station if you want to, all based on MEMS, very low cost. We heard DEM study. How about physical DEM? This is my most recent PhD students. This is a MEMS sensor in there with what we call IMU, inertial motion unit, and then contact force sensors with the MCU inside of it. All the exterior is made with 3D printing. So that measures the contact force and rotation, movement of the sphere. This is what it looks like inside of it. My first encounter of DEM was early 1990, late 1980s. I did DEM simulation of co-penetration test. I don't know if you guys. But anyway, I didn't do anything after that. So this is now I'm back to DEM, physical DEM. This is simple shear test. I'm not going to talk about the details. One major problem is positioning. Theoretically, you can integrate linear and rotational acceleration to get position. No, that's just too much error. So we use we call it ultraband wavelengths to position the sphere, which is still not very ideal. But if we use it to study landslide debris flow, we can probably use GPS. So that, again, GPS become relatively affordable. So that's the future. We just started doing this. Anyway, so that's, I think my timing is up anyway. Well, I'm good. Only 4 minutes out overtime, huh? Thank you. Coffee break, isn't it?
Yeah, so I guess if you have questions, you can